Hello my dear friends, in this video I'm going to show you my latest radio amateur project, my ham radio VHF power amplifier, which is designed for 200 watts and based on transistors. This is the amplifier. I mounted it, but now I'm tuning it. So this is an experiment for me because first of all, it's my first VHF amplifier, and I decided to start with 200 watts. And also, this video is an experiment for me because it's my first English speaking video. I'm not a native speaker, so maybe I'll make some mistakes, so I'm sorry for it, by the way. And also, unfortunately, I am not prepared properly to film this video. One of my Russian subscribers asked me to show the circuit diagram and to make a video about this amplifier, and I made a Russian video, and also I decided to translate it to English, and maybe it would be interesting for English-speaking radio amateurs. The problem is that I also have some work tasks, and radio is just hobby for me. I'm a scientist, but during my free time I sometimes make some radio projects. And as I said before, this is my first VHF radio amplifier. I designed it, calculated. I tried to calculate everything, and I hope that it will work properly. But basically, this amplifier, it's like a typical push-pull amplifier, so it's based on two transistors. I decided to use MRF 9180, and for matching, it uses two microstrip lines, first line and the second line in the output side. And moreover, it's not a microstrip line, it's a coplanar line. And usually I've seen some projects from radio amateurs. I can make a mistake, but yeah, I think from United States I see some videos from radio amateurs, and they made more powerful amplifiers. They made like for 500 watts or for 1 kilowatt, and they used for matching coaxial cables. They used small segments of coaxial cables to match it. Yeah, but when I tried to create to design it, I thought about their designs, but I found one problem, and not only one, two problems. The first problem is that they used coaxial cables with resistance. Unfortunately, I forget the term for the term in English. Maybe it's called not a resistor of a cable, but something like equivalent resistance or something like this. I'm sorry, but they used not the standard 50 ohms cables, but they used 12 and half ohms cables, and I found that it's hard to find such cables. And the second problem was that with that design, it's I tried to calculate it, tried to model it, to try to find optimal lengths of these cables, and I found that it's too complicated. That's why I decided to use a more simpler design to match the input of amplifier and gates of transistor, and also to match an output side with drains of transistors. So this matching networks. I decided to use microstrip lines. I calculated it. I calculated a Q factor and found that it's possible to make it with a high, with not a small bandwidth, with a small Q factor, and it's good because it means that the whole circuit would be stable even with some parasitic capacitance or inductances, or if the tolerance of a circuit will be not so good, but it would be stable in this case. And I'm not confident about the stability of the circuit with that coaxial cable lines, and it's harder to calculate. And also the interesting thing about which I found about this this type of matching is that if you need to fine-tune the transformation, if you need to slightly change active resistance or reactive component, it's easy to do with such type of matching, because as you can see, I use shunt capacitors, and it's possible, first of all, it's possible to move it along the transmission line, so I can change the position of these capacitors, and also I can change the value of these capacitors. And so I can change two variables, and it's enough to fine-tune the impedance, which consists of active component of resistance and of reactance of the circuit of the line. So we need to match two components, active and reactive. And we also could change two variables, capacitance and the position of that shunt capacitors. And I calculate the circuits. I think maybe I can made a more detailed video about it, because it's not so hard, but it's a long topic, and I used a Smith chart. I used some calculation and discussions, of course, with ChatGPT, and after it I calculated these matching circuits, matching networks, and found that if it would be some errors, if it would be a low tolerance, maybe because some problems with mount or some problems with component, I can change, I can significantly change the impedance here, so I can significantly change matching just using moving of capacitor and changing this value. It would be enough to change this impedance significantly and to compensate the error because of low tolerances. So I decided to experiment with these networks, and I'm thinking what I should tell you next, because I'm going to show you the process of tuning the measurement of impedance, because here I use quite interesting technique how to measure it without turning it on, how to create here in this point a good resistance of load to transistor. But also I think before it I should describe you some details from my circuit. Yeah, as I said, it's push-pull amplifier. In the input side I use coaxial balloon. It's a quarter of wavelength balloon made from coaxial cable. Yeah, actually this is a Russian cable, but it's similar to RJ174, I think. Yeah, it's quite similar to it. Yeah, and I use it as a balloon. I have unbalanced input in this side, and then we have two balanced outputs, first and second, and all two outputs are designed to 25 ohms. And then we have a transmission line which I use for matching, and here I will add capacitors at the same way as on output side. Yeah, I'll do it later. And then we have a transistor, and this circuit is designed to create bias voltages on gate sides. And in the output side, everything looks similar to the input side, so we also use the same type of matching lines, but with a little bit different parameters. Yeah, I calculated using online Smith chart, for example, you can check it. And then we have a balloon, but here I use RJ58 cable. It's a little bit bigger, and I hope that it will be enough for my power. I checked it, I calculated it, so it should be enough, but later we will experiment with it. And also the problem with these balloons, it's their geometry. You can see. I'll put my second. I'll try to show you. You can see that this coaxial cable is laying down on the ground plane, and for this type of balloons, that's bad because it significantly impacts on balance. So the capacitance between the how to translate it, not sleeve, maybe external part with this part of coaxial cable should be low with the ground plane. If the capacitance is not low, it would be effect on balance, and these two transistors inside will be unbalanced, and that's good. It could affect on the quality of a signal, it could damage transistors, so it means that it's better to change the position of this line, and I'm going to create on my 3D printer some plastic holders here and maybe here to change the position of this cable. And I'm going to do the same in the output side, yeah, to improve the quality of my balloons. Also, as you can see on the circuit diagram, again, I'm sorry for these paper sheets, but I have no time to do it properly. As you can see on the circuit diagram, here I use Schottky diodes, and this is because of some parameters of this transistor, and this transistor is quite sensitive for negative voltages on gate. So it could be easily damaged if the negative voltage here is applied. For example, if your input signal is big, and if voltage would be negative in this point in the gate, and unfortunately I forget, but you can check in datasheet. I think something like -1 volt or -1.5 volt is danger for this transistor. And that's why I decided to install a Schottky diode here to shunt negative voltages. Yeah, and then I have some RF termination via 20 ohms resistor to ground. Here you can see capacitors to terminate an RF signal. And to this point and to this point I apply bias voltage from my bias source. Yeah, here is the circuit diagram of my bias source. and so I used here Zener diodes and transistor to create 6.2 volts of 6.2 volts, and then I used a resistor voltage divider with thermoresistor to compensate the thermal shift, thermal drift when my transistor heats up. And if you not install this, when transistor heats, the drain current will increase because of heating of transistor, and it could destroy your transistor. So it might be dangerous for transistor, and that's why I installed this thermoresistor, and I calculate these circuits, and when the temperature will rise, the voltage on the gate should become lower. Yeah, and then I have two trimmer resistors to fine-tune the voltage on gates, and without input signal the drain current should be like 700 milliamperes. In this side, the load resistance to a transistor, the RF load, radio frequency, this resistance should be equal to 2.75 ohms, 2.75. So I calculated it, and maybe in next video I'll show you more details how to calculate it. If you are interested in it, please text me under this video, make some comments. Yeah, here I think that it would be a long video if I'll tell you about it in this video. Yeah, but in output side we also have matching lines and then balloon. And to this points I apply a positive voltage on drain, and unfortunately I didn't mention it in this diagram, but to apply this voltage I use this choke, and I use a sandust coil to do it, because it's important to use a sandust here. If you use a ferrite core, it's not good, it's not okay for huge currents and huge DC currents. So you should use sandust coils. Yeah, and here I have some capacitors, some electrolytic capacitor, and I'll apply positive voltage to this point. Yeah, transistor is soldered to this copper plate. Maybe it's not a plate, but it's like a copper bar. Yeah, and here in this PCB, I drilled some holes and installed copper wire and soldered it from two sides to connect ground plane here and here. It's also important when you deal with high frequencies. So along all transmission lines, you can see it's a lot of some drilled holes, and all this device would be mounted on aluminum radiator. Yeah, it has like 12 centimeters on this side and like 20 on between these sides, and I'll attach it here with this screw. Yeah, now I just mounted the circuit. I'm not tested it, of course, and I'm not finished it. I didn't finish the input matching side, I started with output matching. First of all, I'm going to match my 50 ohm output with transistors. As I said previously, I should load my transistor in each side with 2.75 ohms load. But in output side I have a 50 ohms load, like a standard for our devices. After a balloon, I have two resistances, like 25 ohms to this side and also 25 to this side. So this matching circuit should transform 25 ohms to 2.75 ohms on this side of transistor. And first of all, after I mounted it, I'm going to check it without turning off of my device. Is the transformation factor of this line, is it okay or not? And usually for such tasks we use vector network analyzers like this nano VNA, and usually we can apply it from this side and measure the resistance, and if it would be okay, so it means that the matching network is good. But in this case, unfortunately, I can't do it. I can't measure from this side an impedance because the frequencies and because of the problem that I need to match 25 ohms to 2.75 ohm. It's quite low value. It's low value, and some parasitic impedances of my connectors, of my small short wires in this frequency, if I have like half of centimeter wire connected to this port of VNA, it has an impedance like, I don't know, maybe 10 nanohenries, because you can see this two coils, these two chokes each has inductance like 30 nanohenries. So if I attach a small wire, it might have like 5 nanohenry, but it's reactive resistance in this frequency. Reactive resistance, it's multiplication of frequency and inductance. And this reactive resistance would be significant compared to this 2.75 ohms. And I can't measure it because of huge error from this reactance. And it would be significant because of high frequency, of course. So even small inductance is significantly at a huge reactive component. So we can't measure small resistances from this side. Okay, and in order to fix this issue, we might use like a small hack. Here you can see the same line, and from the output side it should be like it should transform 25 ohms from output side to something like 3 ohm in input side. And okay, I can measure from this side the transformation, the impedance, but instead of measuring from this side, I decided to measure from this side. And I disconnected the transistor and attached the resistor here in this side. I can show you it in my PCB. Let me zoom. Yeah, I hope that you can see these two parallel resistors. I attached these resistors and disconnected the transistor here, so it's not soldered to this line. And these two resistors, when it's parallel, it gives me, so it's like 5.6 ohms each, and I have two resistors, so when it's parallel, it gives me 2.8 ohms, so which is quite similar to 2.75 ohms. And now I can mount nano VNA from high Z side, from a site with high impedances, and measure the impedance from this site and tune my matching networks to find a good transformation factor. So I installed resistors here, disconnected the transistor, installed resistors here, disconnected the transistors, and measure my impedance from output side, and trying to match it to 50 ohms. When I'll match it to 50 ohms, it means that my whole output circuit transforms 2.8 ohms from sides of transistors to 50 ohm from output side. And this is my first tuning. It's not precise, it's quite rough, but this is like a starting point. After it, I'll tune it with a power. So I'll apply power and tune it with it, but I decided to start with like a rough tuning. In Russian terminology, a Russian radio amateur called such technique like cold tuning. Maybe if you are English radio amateur, it would be interesting if you will tell me in comments how you called it. Maybe you also call it like a cold tuning when you tune output matching networks without a transistor or without a vacuum tube, but with resistor instead. So now I just mounted all components, and I not tuned this network, and I decided to measure what I receive. I'll measure it with nano VNA, and first of all, of course, you should calibrate your VNA. I done it before, and I can load my calibration, and then I can connect my output side of my amplifier. Oh my god, sorry. Okay. Now we have it. Let's change the frequency. And as I said, we make a VHF amplifier, so we need 145 megahertz. And in this frequency, we have not a 50 ohm. Again, in ideal case, when everything is tuned correctly, we should have a 50 ohm from output side. But in fact, we have like in 144 megahertz, we have like almost 28 minus 32 reactive ohms. So it's not a significant error, because we transformed 2.8 to almost 50. Yeah, we transform it to huge impedance, and if we measure the module of this impedance, so probably it's called not a module, but okay, I'm sorry for some problems with translation, but actually it's a length of a complex vector of an impedance, and the norm of this vector. Yeah, like module that. If we measure it, we have like 42 ohms, so it's not far away from 50 if we compare it with 2 ohms. So we definitely changed the impedance significantly, and we increased it as we wanted. But the wrong transformation might be harmful for our transistors, and it might damage them. So that's why I I'm going to do my best before I turn it on, and in order to do it, I'll change the capacitance and I'll move it along the microstrip line. Probably during my next steps I'll calculate the direction, on which direction and for how long I should move it. I'll calculate the new value of capacitor, and then I'll mount it, and then I'll check. If you're doing some amplifiers and if you can't calculate it, it's also not a big problem. You can just experiment, move these capacitors, slightly change its value, and after a few measurements, after a few steps, definitely you will find the optimal value. But I'm going to calculate and then move in order not to make a lot of soldering points in this line. I'm not going to damage it significantly with my solder iron. Yeah, so I want to reduce the number of steps to find the optimal point, so that's why I'll use more calculations. Yeah, and this is something which we called cold tuning, and after the cold tuning, I'll turn it on, and then I'll fine tune. First of all, of course, I'll measure the input impedance from this side, and I'll match this input transmission lines, these matching networks. So I'll install capacitors here and match it, and after it I'll slightly increase the power, and I found some techniques, some equations how to using like small power, how to calculate is this network load properly or not. Maybe I'll tell you about it in next videos. Yeah, but during the next steps I'm going to turn it on, apply a small power, and maybe slightly fine tune these networks, and then increase the power. Yeah, and that's my plan. Now I'm trying to do it. Unfortunately, I have a lack of time because I need to create scientific papers about neural network, about mathematics. I'm a scientist actually, so sometimes it's hard for me to find the time for my radio amateur projects. Yeah, and I also like to go for a walk, to travel, yeah, to meet with my friends and such activities. So ham projects, it's my hobby. Yeah, and after it I'm going to make a filter, like a low pass filter. Actually, this filter would have like 3 coils and 4 capacitors. So it has an order of 7. Yeah, coils will be installed here, and capacitors are already installed. This is copper plates, and I use them as capacitors. So I calculated the size of these plates to get a needed capacitance. So then I'll tune this low pass filter, and of course it will be connected to the output side of my power amplifier, and then we can test it with huge power. As I said previously, it's one of my first VHF projects. Before it I created some bandpass filters. It's helicoidal filters, so it has 2 coils, one here and one here, and small coupling window inside, so it has a barrier, like a copper barrier, and inside it has a hole to couple these 2 resonators, And to fine-tune these resonators, I used these bolts with some small plates attached inside. So it's like a typical helicoidal filter for VHF, and it wasn't like my first project. And okay, not the first, maybe second. My first project was this antenna. I live in a huge city, I live in Moscow, and the problem is that I can't install antenna in my like modern apartment building. It's illegal. I can use just small temporary antennas, and I attached like a small mount in my outside of my window, and when I need it I can connect the antenna to this mount like this way. And it's a typical dipole. It's small, it's made from telescopic antennas, and I just make something like this, and I have a dipole, and this is a balloon made from 61st material amidon ring. Yeah, and with this setup I used yeah, that's funny, I used a Baofeng portable radio, and yeah, after all losses I had like with that filter installed, I had like 4 watts in antenna, and I successfully told with radio amateurs from different parts of my city. But I'm going to make a radio connection with my father. He's also a radio amateur, and that's why I need more power. And as I said, I have not enough time, and I can make 10 amplifiers for like 10 watt, for 50 watt, for 100 watt. That's why I decided to make like a serious project and made it for 200 watts. Probably I'll not use it with the full power, but at least I have 200 watts, and probably maybe I'll need it one day. Yeah, and I hope that it will be a successful project. My background is like in mathematics and physics. I studied for 2 years in Moscow State University in Faculty of Physics. Yeah, it's like best Russian university. And then I changed the faculty, studied for 5 years as a mathematician, and now I work as a scientist, as a researcher in Artificial Intelligence Research Institute. And so I hope that I calculated it properly, and I can make my first VHF amplifiers for 200 watts. If no, maybe it would be not successful, but I hope that it will be good. And also, if you have maybe some questions or some ideas about my projects, if I'm interesting or not interesting, if you have some feedback for me, I'll be glad to receive it. Please write it in a comment section under this video. Yeah, it would be interesting for me if you have some questions. Maybe I should change something, maybe I should make more video, or not to make a new video. So please write your thoughts under this video. I'll be glad to receive your feedback. So, but with it, I think we can finish for today. Yeah, and thank you for your attention. If it's possible, please subscribe, and bye bye. See you. Thank you.